Hello. Today we will discuss a very important topic in mathematics, and that is the definite integral. We are going to discuss definite integrals. We are going to touch upon the definition of the definite integral, and of course I have written a word motivation. What is the motivation to such a definition, which we will write down. We have not put up the definition on the board up as yet. But there must have been a motivation somewhere at some point of time for which the concept of a definite integral came in. In fact, the concept of integration originated from this fundamental problem. So, I have written the basic problem was to find the area under a given curve, which represents the curve of part of the curve of y is equal to fx. So, this is one border. The ordinate erected at x is equal to a, the ordinate erected at x is equal to b, and the x-axis. This is the x-axis. I repeat, the basic problem was how to find for any given function and its graph, we say area under this curve, and area must have borders. So, here we have four borders. One border is the part of the curve that lies between a and b of y is equal to fx. This is one border. The next border is the ordinate erected at x is equal to a. So, this point a is actually, if we assign coordinates, this point is a, f a. If we assign coordinates to this. This is the line which is the x-axis. Its equation is of course y is equal to 0. And in like fashion, this point has an x coordinate of b. We will come to this part later. And by this reasoning, the coordinates of the point b that we see here is b, f, b. So, having said that, this is the fundamental problem that mathematicians 200, 300, 400 years ago were faced with. How to give a crisp formula for that area. Now, a very simple way of doing it is to take this area and divide the area into n number of vertical strips by ordinates erected at, the first ordinate is at x is equal to a plus h. So, h is the width of each strip. H is the width of each strip. We can write it down here. H represents the width of each strip. So, this ordinate is erected at a plus 2h. So, here we have the ordinate size as fa. The ordinate size here is fa plus h. The ordinate size here is fa plus 2h. The ordinate size here is fa plus 3h, and so on. And the point b, because we have divided this into n equal strips, evidently b must be equal to a plus n widths. So, b is equal to a plus nh, and the previous ordinate here, the abscissa is a plus n minus 1h. So, the ordinate is f of a plus n minus 1h. Now, we will rub out most of the things that appear on the board now, excepting this diagram, because we will have to refer to this in building up a definition for the definite. Now, nobody would disagree that the sum of these n strips will of course be equal to the area. Real area will be the sum of these areas of n strips. But how can we get the value of this particular area, that we'll see there is a very nice way of getting over the problem. We say that the area required A, let's say area required is approximately not approximately equal to here, is equal to sum of the areas of the n strips. So let's see the sum of the areas. We take strip 1 and call it A1. That will be approximately equal to this ordinate into this width. That means we consider it to be of a rectangular shape, omitting the small triangular area. That's why I've used this word A1 approximately equal to H is the width into FA. Similarly, the second strip area A2 is approximately equal to H into F of A plus H. A plus H. This is A2, there is one H here. A3 approximately equal to H F A plus 2H, and we carry on doing this and write the area of the nth strip is approximately equal to H F A plus not NH but A plus N minus 1H, because the last ordinate is F of A plus N minus 1H and that multiplied by H. A plus N minus 1 H. So there we are. Now we see that if we add up all these areas, we get an approximate value of the area that we are looking for, because each strip, though not rectangular, has been considered to be rectangular and the areas have been calculated per strip under that assumption. Now suddenly we find that we do not need this diagram because we've got the areas written down, so we will now rub this diagram out. Now if we take the sum of all these strip areas, we get an approximate value to the area that we are looking for. So we write area required will therefore obviously be approximately equal to H times FA plus F of A plus H plus F of A plus 2H, and we carry on like this till we go to F of A plus N minus 1. This is not X, it is N minus 1 H. So here again the area that we require is approximately equal to, we call it A sub R, indicating that this is the required area. And again I repeat that this is an approximate value. It may be a very close approximation, but it indeed is still an approximate value. It is not the exact value. We will see how to play with this and get the actual area as the limit of a sum. Now this can be compacted into, again approximately equal to H sigma f a plus RH r starting from 0 and r ending at n minus 1. This sigma notation is familiar to all of us. We've learned it in high school. So this value is approximate value. Once again I repeat, the required area can be approximated by this expression. So we will only keep this and this expression and then proceed from there as to how from this expression we can get very good value of the required area. That means a correct value with all the approximations gradually, slain, killed. Now is where the real mathematical reasoning can be injected into this formula, and that is as follows. Now supposing we had divided the area into two strips, then we would have got an approximate value, sum of two rectangles, but that would have been far different from the actual area. So one thinks in terms of then let's say 4 strips or 10 strips or 20 strips. But if we say that we do this, we make n very large. And correspondingly therefore h becomes very small. But we can never forget that n strips together give the difference from A to B. That means the width of n strips, which is nh, must be equal to b minus a. This is very important. Now we can think of this as follows. Supposing there are two people, let's say a husband and wife. The husband's weight is n and the wife's weight is h. The product of their weights is kept constant. So if the husband grows fatter, the wife has to slim down. That is the concept. The product of their weights is constant, which means that if one overgrows, the other has to undershrink, so that the constancy of their weight is maintained. So if we do that, that means we take a very large number of strips of very small width, then we are forced, or we get courage to write that the approximate value of the area, which we don't really need, we can now write that AR no longer approximate is equal to, very boldly, the limiting value as h tends to 0 of h sigma f a plus RH r from 0 r up to n minus 1, and stating in brackets that nh is equal to b minus a. This is a very important requirement. I have seen from experience when students are asked to define the definite integral, they write all this this is equal to limit h. They write all this up to this comma, but they forget to mention this important condition that n and h, they are intricately linked with each other. They are not divorced from each other. They are very, very highly related quantities, and as one goes up, the other shrinks. Now, this being the sum, this being a sum, it is denoted by an integral. One notices that this integral came into mathematics historically as an elongated S. The word sum starts with S. If we pull this up and if we stretch this down, then the limiting position is something like this. It is an elongated S. So, this sum is represented by integral a to b fx dx. So, this indeed forms the definition of the definite integral a to b fx dx. It is defined in terms of an infinite sum, which I have just discussed in great detail, and we gradually move on to other aspects.